Welcome back to my class in number theory. For today, we will take up division algorithm and its proof. But before we do that, we complete first our lesson on floor and ceiling, in particular the decimal representation of a positive integer. Consider the following problem. Prove that if a element of set n is an n-digit number, then n equals the greatest integer function when x is logarithm of a plus 1. The given here is a, an element of set n, and set n is the set of natural numbers or the set of counting numbers. Thus, a element of n implies that a is a positive integer, and that is the first given. The second given is that a is an n-digit number, which means that the number of digits in the decimal representation of the positive integer a is n. And we want to prove that the number of digits in the decimal representation of the positive integer a is equal to the floor of the logarithm of a plus 1. The floor of the logarithm of a is the same as the value of the greatest integer function of x when x is equal to logarithm of a. And we now prove this problem. We start with the given that a is an element of set n. Thus, we let a be a positive integer, that is a is an element of set n. And a is an n-digit number, which means that there are n digits in the decimal representation of a. And we specifically write the decimal representation of a as this number with n digits from a sub n minus 1 to a sub 0. Hence, a in its decimal representation is equal to a sub n minus 1, a sub n minus 2, a sub n minus 3, and the last three digits are a sub 2, a sub 1, and a sub 0, where the first digit, a sub n minus 1, is not equal to 0. Or equivalently, we can write a as a sum of the product of the digits of a and the powers of 10 as follows. Writing a as the sum of the products of the digits of A in the decimal representation of A and the powers of 10, we write A is equal to the first digit of A sub n minus 1 times 10 to the power n minus 1 plus the second digit of A sub n minus 2 times 10 to the power n minus 2 plus the third digit of A sub n minus 3 times 10 to the power n minus 3 plus up to plus is the third digit from the last A sub 2 times 10 squared plus the second to the last digit of A is A1 times 10 to the power 1 plus the last digit A sub 0 times 10 to the power 0 or simply A sub 0. And you can see from this equation that we can derive an inequality with three terms. From this equation, you can see that A, which is equal to this sum of products, is greater than equal to 10 to the n minus 1. We are sure that 10 to the n minus 1 is less than or equal to A. Or A is greater than 10 to the n minus 1 because A has more than one term than 10 to the n minus 1. A is actually equal to 10 to the n minus 1 multiplied by a non-zero digit A sub n minus 1 plus these n minus 1 terms. Therefore, A is definitely greater than or equal to 10 to the n minus 1. But A is less than 10 to the n. 10 to the power n because in the decimal representation of A, the first digit is only multiplied by 10 to the n minus 1 and 10 to the n is greater than 10 to the n minus 1. We take a particular example to show that this inequality is true. Consider the positive integer 23. 23 is a two-digit positive integer because it has two digits, 2 and 3. In this decimal representation of the positive integer 23, the first digit A sub n minus 1 is 2. And the last digit A sub 0 is 3. And 23 as a product of the digits of 23 and the powers of 10 can be written as follows. Hence, 23 is equal to the first digit 2 times 10 to the power n minus 1, where n is 2 because 23 has two digits, n minus 1 or 2 minus 1 is 1, plus the last digit A sub 0 is 3. And you can see from here that 23 the positive integer A, 23, is greater than 10 raised to 1. In this inequality, our A is 23 Our n is 2 because 23 has 2 digits. 10 raised to 2 minus 1 is 10 raised to 1. And here, n is 2 for our example, 23 with 2 digits. And 23, you can see, is less than 10 squared. And this inequality is true for this particular example of positive integer a equals 23. 23 is greater than 10 to the power n minus 1, where n is 2, 2 minus 1 is 1. And 23 is less than 10 to the power n, where n is 2 because 23 has 2 digits. We take another example. In this example, our positive integer a is 10. And 10 has 2 digits, 1 and 0. And 10 can be written as a product of its digit and powers of 10. The first digit is 1 multiplied by 10 raised to n minus 1. For 10, n is 2 minus 1 is 1. Plus the last digit, a sub 0 is 0 plus 0. And from here you can see that the number a, the positive integer a, 10, is exactly equal to 10 to the power n minus 1, where n is 2, minus 1 is 1, or 10 raised to 1. This is an example where a is exactly equal to 10 to the power n minus 1. 10 is exactly equal to 10 raised to n minus 1, where n is 2, or 10 raised to 1. But 10 is still strictly less than 10 to the power n, where n is 2, because 10 has 2 digits. And if we combine these two, any positive integer like 23 and 10, any positive integer a such as 23 and 10 can be less than or equal to 10 to the power n minus 1, where n is the number of digits in the given positive integer. But the positive integer a is strictly less than 10 to the power n, where n is the number of digits in the given positive integer a. And this is just to show that this inequality is true, which we derive from this equation for the expression of a as a sum of the products of its digits and powers of 10. Now we take the logarithm of each term of this inequality. We take the logarithm of 10 to the power n minus 1, the logarithm of a, and the logarithm of 10 to the power n. Taking the logarithm of the terms of this inequality, the logarithm of 10 to the power n minus 1 is less than or equal to the logarithm of a, and the logarithm of a is strictly less than to the logarithm of 10 to the power n. And we apply one of the properties of logarithm to the logarithm of 10 to the power n and to the logarithm of 10 to the power n. By property of logarithm, the logarithm of 10 to the power n minus 1 is equal to the exponent n minus 1 times the logarithm of 10. By property of logarithm, the logarithm of 10 to the power n minus 1 simplifies to n minus 1 times the logarithm of 10, less than or equal to logarithm of a, and logarithm of a is strictly less than 2, the exponent n, times the logarithm of 10. But the base of this logarithm is 10 because without the base, we understood that this is a common logarithm with a base of 10. And the logarithm of 10 to the base 10 is equal to 1. And so this n minus 1 times logarithm of 10 simplifies to n minus 1. Similarly, n times logarithm of 10 simplifies to n because you can check in your calculator, logarithm of 10 to the base 10 is equal to 1. And from there, we will apply one of the alternative definitions of the greatest integer function, or the floor of a real number x. We simplify this inequality by using the fact that logarithm to the base 10 of 10 is equal to 1. And multiply by n minus 1, we get n minus 1. Is strictly less than or equal to logarithm of a, and the logarithm of a is strictly less than n times logarithm to the base 10 of 10 is 1, multiplied by n is 1. Thus, logarithm of a is greater than equal to n minus 1, but is strictly less than n. And to this inequality, we apply one of the alternative definitions of greatest integer function or floor of a real number x. The alternative definition of the greatest integer function of x, where x is a real number, says that if x is a real number, then the greatest integer function of x, or the floor of x, is equal to n if and only if n is less than equal to x, and x is strictly less than n plus 1. You can see that this inequality is of this form, where this integer n is 1 more than, where this integer n plus 1 is 1 more than this integer n. You can see that this integer n is 1 more than n minus 1. If you add plus 1 to n minus 1, you will get n. And comparing these two inequalities, it appears that x is equal to logarithm of a. Hence, using this definition of the greatest alternative, using this alternative definition of the greatest integer function, and with this inequality being true, we conclude that the greatest integer function of the logarithm of a is equal to n minus 1. Comparing these inequalities, x is the logarithm of a, and the integer n here is the integer n minus 1. And this integer is 1 more than n minus 1 because n minus 1 plus 1 is n. And the integer n plus 1 here corresponds to n in this inequality. N plus 1 here is 1 more than n. And using this alternative definition of the greatest integer function, or the floor of x, we conclude that n minus 1, which is n in the definition, is equal to the floor of x, or the greatest integer function of x, where x in this inequality is the logarithm of a. Thus, we conclude that n minus 1 is equal to the floor of the logarithm of a. And from this equation, we transpose minus 1 to the right hand side. Transposing negative 1 to the right hand side, we take the opposite sign of negative and we get plus 1. Therefore, n, the number of digits in the decimal representation of the positive integer a, is equal to the floor of the logarithm of a plus 1, which is what we want to prove in this example. And we have actually used this in the last lesson to find the number of digits in the given positive integer without actually expanding or writing the given positive integer in its decimal representation. We will now define the division algorithm, which is actually a theorem. We now state the division algorithm theorem, and the given in this theorem are two integers a and b, but b is required to be positive, is strictly greater than 0. The theorem says that for any integers a and b, where b is a positive integer, b is greater than 0, there exists integers q and r Q and R are also integers. They can be positive or negative, such that A equals BQ plus R, and R is greater than equal to 0, but strictly less than B. Again, for any positive integers A and B, where B is a For any integers a and b where b is a positive integer, b is strictly greater than 0, there exists integers q and r satisfying the following conditions. A is equal to bq plus r, and r is greater than equal to 0 but strictly less than b. The integer r here is called the remainder, and the integer q here is called the quotient when the integer a is divided by b, which means that b divides a, and so we require that b be greater than 0 because, as we know, division by 0 is not possible, or we cannot divide by 0. Hence, if a is divided by b, b must be positive, must be an integer not equal to 0. But in this theorem, the division algorithm, we further require that b is not equal to 0 and b is positive. And if a and b are two integers such that b is greater than 0 positive, there exists integers q and r such that these two conditions are satisfied. and we write R is called the remainder and Q is the quotient when A is divided by B. There are two important parts or components of the division algorithm which we will also prove, which we will also present in the proof of this division algorithm theorem. The first component is the existence. There exist integers Q and R. Again, the two important components of this division algorithm are the following. First, the existence of integers Q and R. The division algorithm says that there exist integers Q and R satisfying these two conditions. And hence, in the first part of the proof of the division algorithm, we showed that there exists Q and R, a remainder R, and a quotient Q that satisfy these two conditions, which means that we also have to prove that the remainder R is greater than or equal to 0, but strictly less than B. And the second important component of the division algorithm is the uniqueness of the remainder and the quotient. That is, when you divide the integer A by a positive integer B, there is only one remainder. The remainder is a unique integer and the quotient is a unique integer. And to prove that, we will assume that there are two remainders and there are two quotients when A is divided by B. But we will show that these two remainders are equal and the same, and the two quotients are equal and the same. We now prove the division algorithm. For the first part of the proof, we take B as a positive integer. For B greater than 0, that means B is a positive integer, and A is any integer. And these are the two given integers A and B, with additional requirement for B that B should be positive integer greater than 0. And for these two integers A and B, we define Q, the quotient. The quotient is also an integer, which means Q is a whole number, and it can be positive or negative. And we define the quotient Q as the greatest integer function of x when x is equal to A divided by B. We take an example, particular example, to show that the quotient is a positive, is an integer. This example is only given to show you what is meant by this quotient q as the greatest integer function of x when x is divided by b. And for this example, we take a equals 5 and b equals 2. 2 is positive, greater than 0. A divided by b is equal to 5 divided by 2, and it's equal to 2.5. But the quotient we want is the integer or whole number quotient. By this definition, the quotient is the greatest integer function of a over b, and a over b is 2.5. And the floor of 2.5 is the greatest integer that is less than or equal to 2.5. And the greatest integer that is less than or equal to 2.5 is 2. Therefore, when 5 is divided by 2, the quotient q is equal to 2, which is equal to the greatest integer function of x when x is equal to a divided by b. Or the quotient is equal to the floor of a divided by b. In our example, a divided by b is 2.5 and the floor of 2.5 is 2. Therefore, this is the quotient when, the integer quotient when 5 is divided by b, 2. If 2 is the quotient, then what is the remainder? The remainder is obtained by subtracting the quotient 2 means that there are 2. The quotient q equals 2 means that there are 2 units in 5. And multiply this 2 by 2 and subtract the product from 5 and you get the remainder. To get the remainder, we subtract from a, 5, from 5, the product of the quotient and b. And so the remainder is 1. When 5 is divided by 2, the quotient is 2 and the remainder is 1. And we now generalize this result. If an integer a is divided by a positive integer b, the quotient is equal to the floor or the greatest integer function of x when x is a divided by b, and the remainder is equal to a. In our example, a is 5 minus b. In our example, b is 2 multiplied by the quotient 2. Or in general, we write the remainder r is equal to a minus bq, where a in our example is 5 minus b, our b is 2, and the quotient in our example is 2. And it is clear from this equation that if you transpose negative bq to the other side, you will get a is equal to bq. Take the opposite sign of minus bq, you get bq plus r. And this is the first part, the first condition in the division algorithm. If a and b are integers such that b and b is greater than 0, there exists integers q and r such that a is equal to bq plus r. And the other condition is that the remainder r is greater than equal to 0 but is strictly less than b. And we will show that in the second part of the proof. But in this first part of the proof, we have shown that there exists integers q and r. Specifically, the integer q is equal to the greatest integer function of x when x is equal to a divided by b. or the integer q is equal to the floor of a divided by b. And this is our particular example. And the integer r that exists is equal to a minus bq. And we are sure that a minus bq exists because a and b are given. They are integers with additional condition for b greater than 0. And we are sure that q exists and it is actually equal to the floor of a divided by b. And this condition is satisfied for these integers q and r that we have shown exist, and for the given integers a and b. Now we show that the remainder r is greater than equal to 0 but strictly less than b. And to show that the remainder r is greater than equal to 0 but strictly less than b, we again make use of another alternative definition of the greatest integer function. This is the alternative definition of the greatest integer function that we will use for the second part of the proof to show that the remainder r is greater than equal to 0 but is strictly less than b. And the alternative definition of the greatest integer function says that if x is any real number, then the greatest integer function of x, or the floor of the real number x, is strictly greater than x minus 1 but less than equal to x. And for this proof, for this part of the proof, we take x as the floor of a divided by b. Taking x equals a divided by b, we get the floor of a divided by b will be strictly greater than a divided by b minus 1. And the floor of a divided by b is less than equal to a divided by b. We obtain this inequality from this alternative definition of the greatest integer function, where we take x as the real number a divided by b. The floor of a divided by b is strictly greater than a divided by b minus 1, but less than equal to a divided by b. Now we multiply this inequality by negative by minus b, because in the first part of the proof, we take b greater than 0, which means that b is positive. And if you multiply that by negative, minus b will be a negative integer. And if we multiply this inequality by negative integer, we have to reverse the inequality signs. And that's one of the rules, one of the properties of inequalities that says multiply an inequality, both sides of inequality, by negative number reverses the inequality sign. We multiply each term by minus b and we reverse the inequality sign. We start with this term minus b multiplied by quantity a over b minus 1. And we reverse the inequality sign because we have multiplied by negative number. And less than becomes greater than. We multiply this term by minus b. Minus b times the floor of a over b. And again, we reverse this inequality sign because we multiply this by negative, and this becomes greater than or equal to. And we also multiply this a over b by minus b. And we simplify the terms that can be simplified. We multiply each of this term by minus b. If we multiply minus b by a over b over b will cancel out because it's equal to 1. And so minus b multiplied by a over b simplifies to minus a. And negative b multiplied by negative 1 is plus b. Strictly greater than. And here we cannot cancel out b because the b here is in the denominator of a over b and it's in the greatest integer function of a over b. So this term remains as is, minus b times the floor of a over b. Greater than or equal to, and b over b will cancel out because it's 1, and so this term simplifies to minus a. Now we add a real number a to the terms of this inequality, and the inequality will remain the same because it's also one of the properties of inequalities. Adding the same constant to both sides of inequality retains the inequality sign. So we add a to this term, we add a to this term, and we add a to this term, and we simplify. We start with minus a plus b plus a. Greater than minus b times the floor of a over b plus a. Greater than or equal to minus a plus a. And again, we simplify the terms that can be simplified from this inequality. This term minus a plus a simplifies to b because a and minus a are the same quantity but opposite in signs, so they will add up to 0. A minus a is 0, and this term simplifies to b greater than. b is greater than. I will write first the positive term a minus b times the floor of a over b. Greater than equal to minus a plus a add up to 0. But in the first part of the proof of the division algorithm, we define the floor of a divided by b as the quotient q. Thus, this inequality simplifies to b greater than a minus b times q. Greater than equal to 0. But in the first part of the proof, we have shown that an integer r, which is called the remainder when a is divided by b, is equal to a minus b times q. Hence, this inequality becomes B greater than R, and R is greater than equal to 0. Therefore, we have shown that 0 is less than equal to R, and R is less than B. And this completes the second part of the proof. We have shown that the remainder is greater than equal to 0, but strictly less than B. Now, the third and last part of the proof is to show the uniqueness of the remainders and the quotient. We will assume that when A is divided by B, there are two remainders. We denote them by R1 and R2. And when A is divided by B, there are two quotients. We denote them by Q1 and Q2. But we will show that if the remainder and the quotient are unique, we will show that R1 is equal to R2 and Q1 is equal to Q2. First, we assume that there is a remainder R1 and a quotient Q1 satisfying this property. If R1 is a remainder when A is divided by B and Q1 is the quotient when A is divided by B, then by the division algorithm, the remainder R1 is equal to A minus B times Q1. And the remainder R1 is greater than equal to 0 but strictly less than B. And we will assume that there is another remainder R2 and another quotient Q2, satisfying also these conditions of the division algorithm. We assume that R2 is also a remainder when A is divided by B, and Q2 is also a quotient when A is divided by B. Then the following conditions are true if R2 and Q2 are remainder and quotient respectively when A is divided by B. R2 must be equal to A minus B times Q2, and the remainder R2 satisfy this inequality also. R2 is greater than equal to 0 but less than B. But we will show that the remainder R and the quotient Q are unique, which means that we have to show that the remainder R1 is equal and the same as the remainder R2, and that the quotient Q1 is equal and the same as the remainder Q2. Now, subtracting getting the difference of both sides of these equations, we will obtain the following equation. Again, in the second part of the proof, we want to show that the remainder and the quotient when a is divided by 2 are unique. But we will assume in this part of the proof that there are two remainders and there are two quotients, but we will show that these two remainders and these two quotients are equal and the same. Hence, we will show that R1 is equal to R2 if there are two remainders and the quotients Q1 and Q2 are equal and the same if there are two quotients, but we will prove this by contradiction. We will assume that R1 is not equal to R2, and we will show that that will lead to a contradiction. If R1 not equal to R2 leads to a contradiction, then we conclude that R1 must be equal to R2. We want to prove that R1 is equal to R2, but we will do that by contradiction. Hence, we will assume the opposite of R1 equal R2. R1 equals R2 by assuming that R1 is not equal to R2, which means that R1 can be greater than R2 or R1 can be less than R2. But for this proof, we assume in particular that R2 is greater than R1 or R1 is less than R2. Now going back to these two equations, we get the difference of both sides of the equation. We have R1 minus R2 is equal to A minus B Q1 minus A minus quantity A minus B Q2. We get the difference of both sides of these equations. We get the difference of the left-hand sides of the equation, and we get the difference of this side of this equation, A minus BQ1 minus this side, this right-hand side of this second equation, minus quantity A minus BQ2. And we simplify the right-hand side. The left-hand side is as is R1 minus R2. We apply the distributive property of multiplication over addition or subtraction. That is, we multiply each of these terms by negative. We have A minus BQ1. Negative times A is minus A. Negative times negative is positive BQ2. And you can see that A minus A is equal to 0, or A minus A will cancel out, and we get minus BQ1 plus BQ2. And I will write first the positive term BQ2 minus BQ1. And you can see from the right-hand side that there is a common factor between these two terms. The common factor is B, and we factor out B from the right side. The left-hand side is the same, R1 minus R2. Common factor is B. The other factor is obtained by dividing each term by the common factor B. BQ2 divided by B is Q2. minus BQ1 divided by B is Q1. And to this equation, we apply the definition of divisibility, which we have taken in the past lesson. The divisibility has the following definition. We say that the integer d divides n means that n is equal to d multiplied by k, where k is an integer. Again, the integer d divides the integer n means that n is equal to d multiplied by k, where k is an integer. And we apply this definition to this last equation. We now say that B divides R1 minus R2. From this equation, and using this definition of divisibility, we arrive at this conclusion that B divides R1 minus R2, because R1 minus R2 can be written as B times A times an integer. We note that Q1 and Q2 are integers, hence the difference is also an integer. And to this fact that B divides R1 minus R2, we apply the comparison property of divisibility. By comparison property of divisibility, if B divides R1 minus R2, then B is less than equal to R1 minus R2. Again, by comparison property of divisibility, if B divides R1 minus R2, then B is less than equal to R1 minus R2. The last result we obtain is that the difference of the remainders R1 minus R2 is greater than equal to B. And because R1 is a remainder, it satisfies this inequality. R1 is greater than equal to 0 but less than equal to B. And also we take R2 as a remainder, and so it satisfies this inequality. The remainder R2 is greater than equal to 0 but less than B. And we assume that R1 earlier, that R1 is not equal to R2, and in particular we assume that R1 is less than R2. Then from this inequality we transpose R2 to the left hand side, or we subtract R2 from both sides of this inequality. We subtract R2 from both sides of this inequality. We get R1 minus R2 is less than R2 minus R2 is 0. So R1 minus R2 is less than 0, but from here you can see that if 0 is less than equal to R1 and R1 is less than B, then by transitive property of inequality, 0 is less than or equal to B. Also from here, if 0 is less than equal to R2 and R2 is less than B, by transitive property of inequality, 0 is less than equal to B. Or we can omit B, we can omit the equal sign. If 0 is less than equal to R1 and R1 is less than B, by transitive property of inequality, 0 is less than B. 0 is less than B. Or from here, if 0 is less than equal to R2 and R2 is strictly less than B, by transitive property of inequality, 0 is strictly less than B. And from here, if R1 minus R2 is less than 0 and 0 is less than B, by transitive property of inequality, R1 minus R2 is strictly less than B. The difference R1 minus R2 is less than B. And this is a contradiction of the result we obtained earlier that R1 minus R2 is greater than B. Because there is a contradiction that resulted from our assumption that R1 is not equal to R2, then the assumption must be incorrect. Thus, we conclude that R1 must be equal to R2. When we get the difference of both sides of the equations we have earlier, we obtain this equation, R1 minus R2 is equal to B times Q2 minus Q1. But now we conclude that R1 is equal to R2. Hence, if R1 is equal to R2, R1 minus R2 will be 0. And 0 is equal to B times quantity Q2 minus Q1. Now, for this product to be 0, either both B and Q2 minus Q1 are 0, or B is 0, or Q2 minus Q1 is 0. For this product to be equal to 0, both of these factors B and Q2 minus Q1 are 0, or one of them is 0. But B, at the beginning of the proof, is an integer greater than 0, which means that B cannot be 0. So if B cannot be 0 and this product is to be equal to 0, then Q2 minus Q1 must be equal to 0. And that's the only way that the product B times Q2 minus Q1 will be equal to 0, when Q2 minus Q1 is equal to 0. Hence, if Q2 minus Q1 is equal to 0, this implies that Q1, if you transpose this to the other side, becomes positive. Q1 is equal to Q2. Thus, we have shown that if there are two remainders, R1 and R2, and the remainder is unique, then these two remainders are equal and the same remainder. Also, if there are two quotients, Q1 and Q2, and we say that the quotient is unique, then these two quotients, Q1 and Q2, must be equal, as we have shown, must be equal and the same quotient. Therefore, we have shown that the remainder R and the quotient Q are unique integers. And this completes the proof of the uniqueness of the remainder and quotient in the division algorithm. And this also completes the proof of the division algorithm theorem. We now take some examples. For our examples, consider the following problem. Find Q and R of the division algorithm for number 1, B equals 3 and A equals 1 and negative 10. And number 2, B equals 3 and A equals 0, negative 1 and 10. I will answer number 1 for A equals 1 and B equals 3. If B divides A, or if A is divided by B, then there exists Q and R that are integers such that the following conditions are satisfied. If, according to the division algorithm, if A is divided by B, then there exists integers Q and R such that the remainder R is equal to A minus BQ, and the remainder R is greater than equal to 0 and less than B. For these particular values of A and B, we have R is equal to 1 minus B, 3 multiplied by Q. And the remainder R is greater than equal to 0, but less than B, 3. Because Q is an integer, it can be negative, 0, or positive integer. We start with 0 and positive integers. If Q is equal to the 0 integer or the positive integers, then R is equal to 1 minus 3 multiplied by Q. If Q is 0, R is equal to 1 minus 3 multiplied by 0 is 1. If Q is equal to 1, then R equals 1 minus 3 multiplied by 1 is 1 minus 3, negative 2. If Q is equal to 2, R is equal to 1 minus minus 3 multiplied by Q, 2. We have 1 minus 3 times 2 is 1 minus 6, negative 5. And when Q is equal to 3, then R is equal to 1 minus 3 multiplied by 3, or 1 minus 9 is negative 8. But this inequality says the remainder must be greater than equal to 0, but less than 3. And this inequality is satisfied by the values of r, 1, negative 2. Sorry. Among these values of r, only one satisfy this inequality. 1 is greater than 0 and less than 3. But negative 2, the values of r equal to negative 2, negative 5, negative 8 are not greater than 0. So for among these values of q and r, only 0 and 1 are possible. Now we consider the negative integers as values of q. We start with q equals negative 1. If q equals negative 1, then the remainder r is 1 minus 3 times negative 1, or 1 plus 3 is 4. When q equals negative 2, you get the remainder r equals 1 minus 3 times negative 2, or 1 plus 6, 7. When q equals negative 3, we have the remainder r is 1 minus 3 times negative 3, or 1 plus 9 is 10. But this inequality must also be satisfied by r. The remainder r must be positive. These are all greater than 0. But the remainder r must be less than 3. But all of these values of r are greater than 3. So these values of q and r are not possible based on the division algorithm theorem. Therefore, the only values of q and r that are possible are q equals 0 and r equals 1. Now we take a equals negative 10 and b equals 3. The division algorithm says that if a is divided by 3, there exists integers q and r such that the remainder r is equal to a minus bq and the remainder r is greater than or equal to 0 but less than b. For these particular values of a and b, we have r equals negative 10 minus 3 multiplied by q, and r is greater than or equal to 0 but less than 3. Now the values of q are integers. They can be negative, 0, or positive integers. Let us check which of these values of q will give an acceptable values of r. When q is negative 2, the corresponding remainder is negative 10 minus 3 times negative 2, or negative 10 minus 10 plus 6, or r is negative 4. When q is equal to negative 1, the value of r is negative 10 minus 3 times negative 1, or minus 10 plus 3, negative 7. When q is equal to 0, we have r equals minus 10 minus 3 times 0, or minus 10 minus 0 equals minus 10. When q is equal to 1, r is minus 10 minus 3 times 1, or minus 10 minus 3 equals minus 13. And when q is equal to 2, r is equal to minus 10 minus 3 times 2, or minus 10 minus 6 is negative 16. And we can see from the values of r that all of these values of r are less than 3. But they are not positive, they are not greater than 0. Therefore, these values of r corresponding to these values of q are not acceptable under the division algorithm theorem. So for when a is divided by b, there are no positive, there are no integers q and r that will satisfy both of this equation and this inequality. For your practice, please try number 2. Find q and r of the division algorithm for b equals 3 and a equals 0, negative 1, and positive 10. And that completes our lesson for today on division algorithm, but we will take more examples in the next lesson for the application of the division algorithm. If you have question about the lesson today, please ask your question in the comments below. But don't forget to subscribe to my YouTube channel, Art Kalison, the channel of learning and leisure. Thank you for joining me in my class today in number theory.